So today's topic is about magnetic field on the axis of a circular current loop. So we have a circular current loop. So through this loop, current is flowing in this loop. So this is I. The radius of the loop is A. So the current is flowing in this loop and we are considering a point P. We are interested in finding out the magnetic flux density at this point P. Okay, now we take a small current element dl here and similarly dl here also. The distance between this point, say M, and this point P is R, and it is directed towards P, so we say it as R vector. So to view this diagram, you can assume like this, that is, this is circular loop, it's a conductor, current is flowing, okay, and you consider a top one element, current element IDL, and bottom also one element, and the point is here. So the distance between this point M and this point, this length is R, and it is directed towards that point, so it is R vector. And from center to this point, that is this O to P, the distance is D, and this radius of this circle is A. Okay, now we are interested in finding out the flux density at this point. Okay, now one more thing, we have dl vector at this point, okay, top point. So this is here and the r vector is like this, so dl is like this, okay, dl is like this and r is like this. If you consider this plane, so the angle between this dl and r is 90 degree. Okay, that you should keep in mind, because the plane is like this, this dl is here, point is here, so the plane is here. Okay, that means the angle between dl and r vector is 90 degree. So keeping this in mind, we will start deriving to find the magnetic flux density. So what happens is, we know that, but by Biot-Savart's law, the magnetic field, magnetic flux density is given by mu naught by 4 pi I dl vector cross product with r vector divided by r cube. Okay, this is r vector. So this r vector can be represented in terms of magnitude of r vector into r cap. So this magnitude of r vector is nothing but r, so r, this r gets cancelled and then you will get r squared. Now dl vector cross product with r vector. So dl vector cross product with r vector divided by r square. So magnitude of dl, magnitude of r vector, so this value is 1 multiplied by sin theta. I already told you dl cross r is, the resultant is perpendicular, so the angle is 90 degree. So sin 90 is 1, therefore dB vector, magnetic flux density vector, is equal to mu naught by 4 pi I, sin 90 is 1, therefore magnitude of dl, magnitude of r cap is 1, so dl by r square. Now we are interested in finding the r square. So r square is here, this is radius a and the distance here is d. So by Pythagoras theorem, r square is equal to a square plus d square, that is r square is equal to a square plus d square. Therefore in the place of r square, so r square is equal to a square plus d square, so in the place of r square we can write a square plus d square, that is dB vector is equal to mu naught by 4 pi I dl into a square plus d square. Now coming at this point, this is theta, that is this this angle is theta. You have like this, and from dl to point like this. So if you draw the plane, for this plane it is vertical. Okay, now this angle with respect to this plane, circular plane, the angle is theta. Okay, so that's what is written here, it's theta. That means this is 90 degree, so this will become 90 theta So these two angles put together is 90. So this will be 90 minus theta. This is 90 minus theta. So if you draw a line like this, this will be 90 minus theta. But this one and this dB vector is perpendicular, because we know that dl cross r vector is perpendicular. It is 90. Okay, that is, this is 90. Since this is 90 minus theta, this is theta. Okay, so this is for this direction dB. If you consider this similar point diametrically opposite, then the direction will be, dB vector will be in this direction. So now we know everything. This is theta, this is dB. Okay, now we will resolve into horizontal and vertical components. So this is dB and the angle is theta from this point. Okay, now this is x, this is y. Cos theta is adjacent side by hypotenuse, which is x by dB. Now x, that is x is equal to dB cos theta. So this horizontal component is dB cos theta and vertical component is dB sin theta. One important point is, since you are considering a circular loop and a point, the horizontal component gets added up, whereas vertical component, if you consider this, it will be this side, and if you consider this component, it will be opposite. So diametrically, magnitude wise, both are equal and opposite direction, therefore it is 0. Similarly, for each and every point, if you resolve into horizontal and vertical components, the vertical components gets cancelled out. Only the horizontal components gives the magnetic flux density. Vertical components gets cancelled out. Therefore, you need not consider about this dB sin theta. Only you have to concentrate about dB cos theta. Okay. Now we have dB is equal to, from that equation, mu naught I by 4 pi dl by a square plus d square. Now the horizontal component is multiplied with cos theta. So from this triangle, if you see cos theta is the adjacent side by hypotenuse. Adjacent side A and hypotenuse is r square is equal to a square plus d square. Therefore r is equal to root of a square plus d square, that is a square plus d square plus half, that is cos theta. So the same diagram I have drawn here, AD, and this is hypotenuse, root of a square plus d square. So cos theta is a by, that is adjacent side by hypotenuse, root of a square plus d square, which is nothing but a square plus d square power half. That's what is written here. Now this is power 1, this is half, 1 and half. 1 and half is 3 by 2. Now I dl a. Now this is due to this point. Now we have to consider the entire loop. So therefore we go in for integration. The question is, if you are multiplying by cos theta and here also cos theta, forget about that cos theta. The remaining terms you will be having only dB. So if you want total all around the loop, then you are integrating both sides. In that case, you are multiplying cos theta that side and cos theta that side, and we have made it as an equivalent form. Therefore it is enough if you integrate the right hand side of the equation alone. So if you go for integration, this dB, integral dB will be b. Okay, so now you have 0 to 2 pi a. What is 2 pi a? 2 pi a is the circumference of this circle, where a is the radius, 2 pi r. So here a is the radius, so 2 pi a. So lower limit is 0, upper limit is 2 pi a. Mu naught I a by 4 pi a square plus d square power 3 by 2 into dl. That's what the result we got it here. So this integration with respect to dl. So mu naught I a divided by 4 pi a square plus d square whole power 3 by 2 is taken outside. In the integral you have dl. Integral dl is L. So upper limit is 2 pi a, lower limit is 0. Therefore L value is 2 pi a. You have to substitute 2 pi a. Now if you substitute L is equal to 2 pi a, you will be getting B is equal to mu naught I a by 4 pi a square plus d square power 3 by 2 into that L. L is 2 pi a. Now you can do the simplification. Pi gets cancelled. This 2 is 2. So therefore magnetic flux density for the entire circular loop carrying current I is given by mu naught I a square, where a is the radius of the circular loop, divided by 2 into a square plus d square whole power 3 by 2. Now we have to consider two cases. One is what happens if this distance slowly shrinks and comes to 0. That is one case. And another case if the d is at very far distance. So that two cases we have to analyze. Now we will deal with two cases. Case 1 is you have a distance, that a point of consideration is at a distance of d from the center of the circular coil. Now you make this piece slowly decreasing and one point it becomes 0. That means d value equal to 0. So case 1, if d equal to 0 means we are considering at the center of the coil. So what happens is this value becomes 0. Therefore b is equal to mu naught I a square by 2 a square power 3 by 2. Since d is 0, so this 2 gets cancelled. So you have mu naught I a square by 2a cube. Okay. Now this a square and this will go. Therefore, b is equal to mu naught I by 2a. So this is the magnetic flux density at the center of that circular coil, which is given by mu naught I divided by 2a. So two things we have to keep in mind. If the current increases in the circular loop, magnetic flux density also increases. At the same time, if the radius of the coil, that is a, increases, then the flux density decreases at the center of the coil. This is one observation. Now case 2, we will go for case 2. So case 2 is the d, this distance, that is you have a circular loop and we are considering a point here. Assume this point is at very far, very far compared to this radius. That means now radius becomes negligible. A, that is d is very much greater than a. So this is case 2. So what happens is this term will become negligible. Therefore, magnetic flux density is equal to mu naught I a square by 2. Now since a is negligible, this term can be equated to 0, d square power 3 by 2. Now these two terms gets cancelled, then the magnetic flux density is equal to mu naught I a square by 2d cube. Okay, 2d cube. Now if you carefully see the magnetic flux density, it depends on the current. So now we are interested at the distant point, very far point. The magnetic flux density at that point, because of the circular coil, it depends on the current through the coil, radius, but radius is very small. Okay, and this term is divided by d cube. That is, if this is going to be 10 meters, 10 into 10 into 10. So that means this value will be very high. Therefore, magnetic flux density greatly decreases. That is, magnetic flux density is inversely proportional to d cube. This is very important. So that's where d is the distance between the center of the circular loop and the distant point. It is at very far. So these are the points we have to remember when we consider for a current carrying coil and we are interested in finding out a magnetic field at some point and at the center point of the circular loop. And the third case is at a very far distance. In that case, this r will become negligible and we have only that d, this term, and this value is very less. Okay. So in this case, last case, we saw that magnetic flux density is inversely proportional to d cube. So that's all about magnetic field on the axis of a circular current loop. Thanks for your attention. Thank you. Nandri.